Hi, my name is Jason Orender. I am the primary author of Anytime Rule Compression and Rectified Logistic Modeling for longitudinal signals. My co-authors are Jiangwen Sun and Mohammed Zubair, and we are from Old Dominion University. Our motivation for authoring this paper was to produce interpretable longitudinal models, specifically in high-stakes longitudinal sensor monitoring situations where you have like a clinical or industrial setting. End users have to understand why a prediction or alarm is triggered, not just the fact of the alarm or prediction. The L1 regularized logistic regression is often sparse and can perform this role, but they still can have lots of small coefficients that obscure um, the uh, um, the final logic of how the model works. Um, what we want is a compact rule list with a balanced sensitivity and specificity. We use UDensJ because it's good at um, uh, imbalanced data sets, and we also use a high area under the ROC curve. I'll give you a quick overview of our approach. We rectify the raw longitudinal features into binarized plus minus one form. Uh, how we do this is covered in our previous work, so I won't waste time covering that here, but we will look at a simple version of this binarization process in the next couple slides. We then train the L1 regularized logistic regression baseline on those rectified features. And you see, even that in and of itself can bring out the true support. We then apply the logic policing step, which is what this paper is addressing, to compress the coefficients into a simpler rule list. And we can tune that rule list to preserve a maximum UDensJ or metric of your choice at the chosen operating point. The anytime property describes when you reach that acceptable simplicity accuracy trade-off. Here is the algorithm, or at least the simplest version of the algorithm that we can use to binarize. So given a number of sensor signals, we can avoid raw time series and ad hoc temporal features. Then we derive a critical range from the positive class examples and code each of those binarized representations as a +1 if it lies within the critical range and a -1 otherwise. And then I'll cover the critical range intuitively on the next slide. Naturally, binary or categorical features are trivially mapped, and the result is we have a uniform binary input space with direct logical semantics. Intuitively, we can take a sensor reading and note which time steps an event occurs on. Then we can mark the top and bottom of the range at which this event occurs, and then we're going to call this the critical range. A relevant feature will look like the top of that figure to the right, and then an irrelevant feature would look like the bottom. So the relevant feature will have a narrower range than the full range, and the irrelevant feature will look like the critical range covers the entire range. This can be leveraged to pick out which features are relevant, or at least a subset of which features are more likely to be relevant, and generate an interpretable model that can reproduce the events. When the model is ultimately fitted, the ones that look like the top will get the non-zero coefficients. That would be a necessary but not sufficient condition. One of the things that we did to allow us to assign large non-zero coefficients to the polished features was that we used a mean matching intercept. Essentially, we fit the L1 regularized logistic regression model on the rectified features, and then we use that intercept so that the logit at the mean feature vector matched the class log odds. This anchors the model to the empirical prevalence of the positive class. And what we're calling empirical prevalence is the number, essentially the number of positive examples over the entire data set. And then the L1 regularization yields a sparse coefficient vector beta over the rectified inputs. And we have a custom solver that exploits the binary structure for faster coordinate descent training. I'll show you just how much faster in one of the later slides. The logical polishing takes over from after we have fit the weights to the rectified data. Over to the right, the top plot is the non-polished coefficients. So we still have lots of small, low magnitude coefficients, and they are close to, but not the ground truth feature set. We treat each non-zero coefficient as a candidate rule condition, and then we sort the magnitudes so that we can test them one by one in order, and then incrementally build the rule models using the top K features and evaluate our metric, which happens to be units J. And then we adopt that compressed rule model if J stays within a relative tolerance to the baseline. And then we can select which features get us to the minimum allowed metric, thus satisfying the anytime condition. The final rule model has K number of rules derived from the top coefficients of the logistic baseline. And then the prediction is positive if at least M of the K rules fire. So we're calling that M of K voting. And the global K, which is the size of the coefficients that are assigned, controls the size of the rule set. We tested 3, 5, and 10. The threshold, M, is chosen to maximize J on the validation data. And that J threshold can be anything that you choose. For instance, if 8.8 is enough, you only need 4 of those coefficients in your rule set. The experiments show a robustness across K and full adoption. So you can have any K that you want as long as you're setting the intercept correctly, as we stated previously. Our experimental setup was essentially a synthetic longitudinal data set with known ground truth logical rules. It was meant to simulate a set of sensor readings that cycled over random time periods and was continuous along the entire data set. We had multiple data set sizes from 5,000 to 10,000 examples, and the baseline for what we're considering correct is the sklearn package in Python. Our proposed improvement was the rectified data plus the custom solver, both with and without logical polishing. And if you look over to the right, you see that the p-value comparison shows that our methods are all functionally equivalent. It's just that the the proposed improvement gives better um, uh, solving times and also um, improved interpretability. All right, so I'll go over some of the improvements that we saw. It was up to a 50 times reduction in model complexity after logical polishing. Some examples are for n equals 5,000, meaning that we had 5,000 examples. We had 344 non-zero coefficients before the polishing commenced, and then 7 rules after. And then similarly, we got 349 to 7 and 257 to 8 with different counts. So we showed a consistent set of improvements. The rule lists are short, 7 to 8, and human readable, and they capture a core decision logic that is easy to understand. The Udens J preserved or modestly improved relative to the logistic baseline, and the AUC was essentially unchanged at 0.1 to 0.3%. Additionally, for runtime and scalability, we have a custom solver on the rectified plus minus one features, which takes advantage of that binary nature and is about 1.5 to 2.3 times faster than the sklearn on those large data sets. The sparse binary representation also reduces the memory footprint, so you can run larger matrices. The logical polishing step, while it does take a little extra time, adds only fractions of a second to the training, and also the amount of interpretability that you gain is far outweighed in most cases when you do the logical polishing. We didn't get any evidence of overfitting when we did the compression. The rule models sometimes generalized even slightly better. And the approach scales well to larger longitudinal sensor data sets since the rectification itself is linear in time and the custom solver tends to increase its advantage over sklearn even the larger the data gets. So in conclusion, we have an anytime logic polishing which converts rectified L1 logistic models to a compact set of rule lists, and it preserves the best attainable balance of sensitivity and specificity, as well as maintaining the area under the curve essentially unchanged while reducing the model complexity by up to 50 times. The custom solver that we alluded to for binary inputs accelerates the training with a little overhead for polishing. Usually it's not significant. And it provides a practical path to interpretable models for longitudinal sensor monitoring. Now, I did in several cases say that the custom solver is faster than sklearn. Just keep in mind that the custom solver is very focused and specific to take advantage of those binary inputs, which is why it's able to achieve those increased speeds. Thank you for listening to my talk, and if you're interested in further correspondence, we have our contact information on the paper, and I would encourage you to contact us, and I can point you to the GitHub where the custom solver is located. You can install it just like any other Python package. Thank you.